Hello. In this lecture, we're going to be talking about waves on the sea surface. So, waves are nothing more than energy moving across the surface of the ocean. The seagull in the figure on the right-hand side demonstrates the motion of the water molecules in the water as a wave passes by. Here, see the wave is moving in this direction, and as the wave approaches, the seagull actually begins to move toward the wave. As the crest of the wave, which is the highest point in the wave, begins to move closer to the seagull begins to move upward. As the crest approaches even closer, the seagull continues to move upward, and then to the right in the direction the wave is traveling, so that whenever the seagull is directly, or I should say, whenever the crest is directly under the seagull is moving in the same direction as the wave. And as the crest begins to move out from underneath the seagull begins to move downward, and then as the bottom part of the wave, known as the trough, moves under the seagull moves once again in the opposite direction the wave is traveling. So this circular path that the seagull moves through as the wave moves past the seagull is the same path which all the individual water molecules move through as a wave moves by. So here we're going to look at the anatomy of a wave, the parts of a wave. So waves are undulations in the sea surface. The highest point of a wave right here is known as the crest, and the lowest parts of a wave are known as the trough. And the distance between two consecutive crests or two consecutive troughs is known as the wavelength. So here's the wavelength, the distance between this crest and this crest. Wave height is the vertical distance between the bottom of the trough and the top of the crest. That's the wave height. Waves can be characterized using frequency, which is the number of waves or wave crests that pass a particular point in 1 second. Okay, so if, say for example, one wave passes by point A every second, then that wave is said to have a frequency of 1 wave per second, which is 1 hertz. Let's say if 2 waves would pass by every second, it would have a frequency of 2 waves per second, or 2 hertz. Let's say if 1 wave passes by every 2 seconds, that means for every 1 second, half of a wave passes by, and that the wave would have a frequency of 1/2 wave per second, or 0.5 hertz. The period of a wave is the inverse of the frequency, which means it's the period of time it takes for 1 wave to pass by. So let's say if we're looking at location A, and if it takes 1 second for a wave to pass by from crest to crest, that wave has a period of 1 second. If it takes 2 seconds for a wave to pass by, that wave has a period of 2 seconds. And if you note, a wave that has a period of 2 seconds, so if period t equals 2 seconds, and the frequency of that wave, f, is equal to 1 divided by the period, which is equal to 1 divided by 2 seconds, which equals 0.5 hertz. Just as we said before, if one wave passes, if it takes 2 seconds for a wave to pass by, it has a period of 2 seconds and a frequency of 0.5 hertz. Hz is the abbreviation for hertz. So another example, if if a wave has a period of 10 seconds, so let's say that it takes 10 seconds for one full wave to pass by, that means that it has a frequency of 1 over 10 seconds, which is 1/10 hertz, which makes sense because in every 1 second, 1/10 of a wave will have passed by. So we can characterize waves using either period or frequency. And period and frequency are inversely proportional to one another, or inverses of one another. So if the wave has a very high frequency, means that there's many waves per second, then the time period for each wave must be very small, so it has a small period. So a large frequency, small period. Conversely, if a wave has a very small frequency, there's very few waves per second. That means that it takes a long time for that wave to pass by, so it has a large period. So if a wave has a high frequency, it has a small period, and if a wave has a small frequency, it has a large period. And here, once again, we have illustrated that circular path in which the water molecules rotate through as the wave passes by. It's important to note that as a wave passes by, water is not moving with the wave. So waves coming to shore do not bring water to shore. Waves move through the water. Okay? And so, say if we look at a water molecule, it will move through this circular path. Change the pen color here. It'll move through this circular path, this water molecule. So whenever a crest is here, the water will be at the top of this circular path. And whenever a trough is located here, the water molecules will be at the bottom part of this circular orbit. So for example, right here, the water molecules are at the bottom part of this circular orbit. Or the water molecules here are at the top part of the circular orbit because there's a crest here. And so the water molecules just rotate around and around and around as wave after wave comes through. Water itself isn't moving. So here, the distance from one crest to the next is the wavelength. And we'll notice that at a depth equal to half of the wavelength, we have the water being disturbed by the wave passing by. But at depths greater than half the wavelength, there is no disturbance in the water. So waves, only water within the depth that's equal to half of the wavelength is disturbed by a particular wave with that wavelength. So for example, if this wavelength was, say, 6 meters, then the water disturbed by this wave would only extend down to 3 meters. So if you were a scuba diver swimming down here at 4 meters, you would not perceive this wave passing by at all. But if you swam up to a depth shallower than 3 meters, you would perceive that wave. Here's a table of different types of waves: their disturbing force, restoring force, and a typical wavelength. So, as I said, waves are energy traveling across the surface of the ocean. The energy is imparted into the sea surface by some sort of disturbing force, and it's the restoring force, which is a force that's trying to bring the sea surface back to its original undisturbed state. And so that's what allows the wave to travel, is the restoring force. So for example, for a wind wave, wind blowing over the sea surface is what disturbs the sea surface. So you have flat sea surface, wind blows over it, and it creates a pile of water. Now that pile of water is disturbed by this disturbing force of the wind. Okay, so that's what disturbs it. Now this gravity then pulls this water down. Gravity is the restoring force. This water moves down, but it overshoots the original flat location that the water was in, and it goes down too far, forming a trough. So the water is like, wait, you're down too far. The water pushes back up against the trough. Water is then pushed up, but it overshoots again, and it forms a new crest. And so the restoring force, constantly trying to get the water back to its undisturbed state, is always overshooting, and that's what allows the wave to travel. So for capillary waves, these are very small waves created by wind. The restoring force is actually the intermolecular attraction between the water molecules. So the waves are small enough that the force pulling the water in the crests down is actually the attractive forces between the water molecules. And this occurs for waves with wavelengths up to and including 1.73 centimeters, so fairly small waves. But once the wavelength exceeds 1.3 centimeters, then the restoring force is gravity. Okay, so basically the waves are large enough that the intermolecular forces between the water molecules is negligible, and the primary force moving the water is pulling the water down from the crest is gravity. So all other waves have gravity as a restoring force. So we have wind waves disturbed by the wind, seiches, which are disturbed by different phenomena, changes in atmospheric pressure, a storm surge, or tsunami, seismic sea wave, which is a tsunami, which is caused by basically a large displacement of a large volume of water over a short period of time, which could be a faulting in the seafloor, or volcanic eruption, or a landslide. And the tides are disturbed by the gravitational attraction of the moon and the sun and the rotation of the earth. And the typical wavelengths of these waves, as we said, capillary waves are up to and including 1.37 centimeters. Wind waves typically are between 60 and 150 meters. Seiches are variable. It depends on the size of the basin in which they exist. Tsunamis have a typical wavelength of 200 kilometers, 125 miles. And tides, they have a wavelength of half of the Earth's circumference, because there is a tidal bulge or a crest on each side of the planet, so the distance between the two is half of the circumference of the planet. So this chart shows us how much energy in the sea surface is in each type of wave. See, most of the energy is in the form of wind waves. And then the second is in the tides. There's a 24-hour period tide and a 12-hour period tide. So that means that most disturbances in the sea surface are due to wind waves and the tides. Now we're going to look at the difference between deep water and shallow water waves. A deep water wave is a wave in which the water depth is greater than half of the wavelength. So here L is the wavelength, the distance between two crests. This dashed line represents half the depth equal to half of the wavelength. This is a deep water wave because it is in water deeper than half the wavelength. So this wave, the water moving as the wave passes by, does not interact with the seafloor whatsoever. So this is known as a deep water wave. And as deep water waves move towards the shore, the water depth decreases, and eventually the wave will enter water whose depth is less than half the wavelength. Whenever the wave is in water less than half of the wavelength in depth, the water molecules that are moving in a circular orbit, they begin to interact with the seafloor, and the wave feels the seafloor, and that causes changes to occur in the wave. And any wave that is in water less than half of its wavelength in depth is known as a shallow water wave. So deep water waves that are in water that's deeper than half of its wavelength, and shallow water waves that are in water that's shallower than half of its wavelength. And the difference is that shallow water waves interact with the sea floor, where deep water waves do not. Only capillary and wind waves have a short enough wavelength that they can be deep water waves. All other waves have long enough wavelength that they always interact with the sea floor. So how are waves generated? Well, whenever we have undisturbed water, so flat undisturbed water, the wind begins to blow over it. The wind and friction between the wind and water will cause water to pile up. Okay, now this pile of water, this is the beginning of a wave. This is a crest. And if it's small enough, the intermolecular forces in the water will pull the water in this crest down, and that will be the restoring force. That's what makes it a capillary wave. And the wind blowing in this direction will begin to move the wave in the direction of the wind. And also, whenever the wind blows over this little crest, the wind slightly eddies downwind of the crest, and that eddy creates a region of slightly lower atmospheric pressure than everywhere else around it, and so that means there's higher pressure on the upwind side of the crest than the downwind side of the crest, and that difference in pressure also pushes the wave crest in that direction. So the wind disturbs the sea surface, it creates the crest. The crest then is pulled down by the intermolecular attraction of water molecules, which creates a trough, and the trough is pushed up. Same reason, creates a new crest. So that's the restoring force causing the wave to undulate, and it's the wind blowing that pushes that crest along, and it's that slight difference in pressure that also pushes the crest along in the direction of the wind. Now eventually, as the wind continues to blow, these waves will grow in size. They'll increase in wavelength, increase in wave height. Once the wavelength equals 1.74 centimeters, the force of gravity is dominant as a restoring force rather than the intermolecular forces between water molecules, and the capillary waves transition into gravity waves, also known as wind waves. And as the wind continues to blow over these wind waves, they will continue to grow in size. Okay, until eventually there is a maximum height that wind waves can develop for a given wavelength. So the ratio of wave height to wavelength is maxed out at 1 to 7. So a wave cannot grow higher than 1 unit if its wavelength is 7 units long. For example, if a wave is a wavelength of 7 meters, the maximum wave height of that wave would be 1 meter. If the wavelength was 14 meters, the maximum wave height would be 2 meters. And what happens is, as the wave height grows and approaches that ratio 1 to 7, the crest becomes pointed, and the wind begins to blow water off this point, and that forms a white comber, as you see here. So this is where the steepness, the ratio of height to length is approached 1 to 7. So now we're going to talk about how waves move. So whenever waves are generated by the wind, they begin to move, travel through the ocean. And the speed at which a wave travels at is determined by its wavelength. So waves with longer wavelengths travel faster than waves with shorter wavelengths. And whenever these waves are all different wavelengths are generated by the wind, and as they travel, they begin to separate, where the longer wavelength waves travel faster and they pull out ahead of all the other waves. And so you begin to have this grouping of waves of similar wavelength, where the longest wavelength waves are out front, then you have slightly shorter wavelength waves behind them, slightly shorter behind them, slightly shorter behind them. And whenever the waves separate into groups of waves of different wavelength, that's called dispersion. Dispersion is a phenomenon that occurs as waves separate because waves of different wavelengths separate because they travel at different speeds or velocities. Whenever this dispersion occurs, we get these groups of waves of similar wavelength, and that's called swell. Swell. And the swell is when you have the consistent waves of similar wavelength passing by. And when these groups of waves of the same wavelength are known as wave trains that travel. So here's a wave train right here. There's these 5 waves of similar wavelength. And you'll notice that the group of waves, the wave train, travels at one speed, and individual waves within it travel at a different speed. This is interesting. This is called group and velocity and celerity. Group velocity is the speed at which the group of waves travel at, where the celerity is the speed at which an individual wave within the group travels at. So let's look. So this red line marks the front of this wave train, and this black line, marks the position of this this individual wave, wave number 5, is colored red. As we want to see, each figure is a later snapshot in time as we go down. So here we can see the wave train has advanced, as well as that individual wave within the wave train has advanced. And over time, they move forward. And you can see that the wave train has moved up to this point, so has traveled this distance in this amount of time. And the individual wave, wave number 5, has traveled this distance in the same amount of time. So the individual wave has covered a much larger distance than the wave train itself in the same amount of time. So that means that the celerity, the speed of an individual wave, is faster than the actual speed or velocity of the group of waves. So what this means is that since the individual waves are moving faster than the group that they're in, waves must disappear at the front and appear at the back. And that's what happens, because each wave imparts half of its energy into the wave in front of it and half its energy into the wave behind it. So at the very front, say wave 1, it gives half of its energy into the wave in front of it where there's no wave, and half of its energy behind it. So it gives away all its energy, but it doesn't get any energy because there's no wave in front of it, so it eventually disappears. Where 2 got half of its energy from the wave in front of it, wave 1, and half energy from wave behind it, wave 3. So it gave away half of its energy. It gave away its energy to the wave in front of it and behind it, and it received energy from the wave in front of it and behind it, so it remained intact. But eventually, whenever 2 is in front, it gives away half its energy to 3 and half its energy to the water in front of it. But it doesn't. It only gets energy from the wave behind it, 3, and so it eventually phases out. Where new waves phase in at the back of the wave train. So individual waves disappear at the front of the wave train, and new waves appear at the back of the wave train. And this is because the speed at which individual waves travel, the celerity, is faster than the speed or the velocity at which the wave train or the group of waves travels at. Now, deep water waves, the individual waves themselves, they travel at a celerity or a speed that is equal to the wavelength divided by the period of the wave. Now, since the wavelength is usually a function of the period, we can say that the celerity is, in metric units, usually about 1.56 times the period in meters per second. So let's say if a wave has a period of 5 seconds, that means that it's going to travel at roughly 7.5 meters per second. And in English units, if a wave has a period of 5 seconds, it's going to travel at roughly 25 feet per second. For shallow water waves, the speed at which the individual wave travels is not a function of its period, but rather a function of the depth of the water, d. And the speed is equal to the square root of the acceleration due to gravity, which is a constant, times the depth of the water. So now you can factor out that square root of g, which is a constant. That just gives you 3.1. And so the speed is equal to 3.1 times the square root of d in meters per second. So let's say if the depth of the water was 4 meters, right? The square root of 4 is 2. 2 times 3.1 gives you 6.2. So the speed of a shallow water wave in 4 meter deep water would be 6.2 meters per second. Here we can see mature wind waves off the coast of Oregon, and this is a swell. So you can see what a swell is. Here's a crest, here's a crest, here's a crest, so these crests these waves are of uniform wavelength. So they have this, because of dispersion, these waves have separated from waves of different wavelength because all these waves are traveling at the same speed. It's almost like in a marathon. All the runners start from the same place, the starting line. Just like all waves start from the same place, wherever the wind is blowing over the water generating the waves. But once the race starts, the fastest runners move out to the front. As the race starts, the longer the race goes on, the more the runners separate. The faster runners move out to the front. The middle speed runners find themselves in the middle, and the slowest runners are at the very end. And the distance between those runners increases as time goes on, and the runners separate more and more. That's what happens to the waves. The longest wavelength waves travel the fastest, so they pull up front, and the shortest wavelength waves travel the slowest, so they are lagging behind. And so as we move away, we'd expect the wavelength of the waves to decrease with distance because the shorter wavelength waves are slower and are coming up behind the longer wavelength waves. We expect the wavelength to decrease as we move in this direction, assuming that the waves are traveling in this direction. So what influences the size of wind waves that can develop? Well, there's three factors. The wind strength, that is the speed of the wind, basically. The wind must be blowing or moving faster than the wave crests are going in order for energy to be transmitted from the wind into the wave. So if the waves are traveling at a speed faster than the wind is, then the waves won't grow in size. The wind duration, this is the amount of time in which the wind blows over the water. If the wind blows over the water for a short period of time, it will not generate large waves, but if the wind blows over the water for a long period of time, it will generate large waves. And finally, there's the fetch. This is the uninterrupted distance over which the wind blows without changing direction. And so the larger the fetch, the larger the waves that can develop. And so these three factors determine what size of waves that can develop. And sailors often take these three conditions into consideration when determining the maritime forecast. And so if you ever listen to the radio and you get the maritime forecast, that is the wave size is usually predicted given the wind strength, how fast the wind is blowing, the wind duration, how long it's blowing at that speed, and the fetch. And that's determined by which direction the wind is blowing. So in the case of Narragansett Bay, since it's longer north to south and is east to west, if the wind is blowing north to south, it's going to blow over the water a longer distance than if the wind is blowing east to west. So if you have a north to south or south to north wind, you're going to have a larger fetch than if you have an east to west or west to east wind over Narragansett Bay. And so those north to south or south to north winds are going to have a larger fetch and therefore be able to generate larger waves in the Narragansett Bay than east to west or west to east winds will. And a fully developed sea is the maximum wave size possible for specific wind conditions, that is for a particular wind strength, duration, and fetch. And so how wind wave development occurs, so you have undisturbed water, the wind begins to blow over it, it creates these little capillary waves that grow in size into wind waves. And the region where you have active wind wave development, that produces eventually from ripples to chop. Okay, And the chop is when you have all waves of all different wavelengths at the same location. And so you just have this irregular up and down, this very choppy water. So choppy waters occur where the wind is actively forming waves. But once the waves travel out of the region where waves are actively being developed, and we have these fully developed seas, the waves will then begin to separate, where the largest wavelength waves, they are the fastest, they travel out first, and then the second longest, and the third longest, and eventually the shortest wavelength waves will leave. And so the waves will be separated in groups of similar wavelength, forming the swell. Okay, and remember, this process of the waves separating based upon wavelength is known as dispersion. So the longer this fetch is, the longer the distance over which the wind is blowing over the water, the larger the resulting waves will be. The faster the wind is blowing, the larger the waves will be, and the longer the wind blows, the larger the waves will be. So if you ever notice, if you go to the beach or if you're near the water on a stormy day, the water looks all choppy, and that's because waves are actively being formed on the water because the wind is blowing over the water. If it's a very nice day, calm day, there's not a lot of wind, you'll see these nice waves, or in other words, the swell, where you'll see waves of similar wavelength, because those waves are generated somewhere else where the wind was blowing over the water and have traveled and dispersed through what's called dispersion. And so we're getting waves of uniform wavelength in the water. Here's a map of global wave heights. The color represents the wave height, and red is highest, and then you get the lowest until blue and purple are the lowest. You see we have the largest wave heights down here, and that's because up here we have westerly winds that blow from west to east. Okay. And then we have the easterly winds, here that blow from east to west. And in the northern hemisphere, we have the easterly winds in the southern hemisphere. But both these northern westerlies and northern easterlies and these southern easterlies, they are disrupted by the continents. So the distance that the wind can blow over the water is limited by the presence of continents. But these westerly winds down here, see, they can blow over the water for a long distance, and the only disruption is this little bit of South America. And so you can see you have the smallest wave height just over here because this disrupts the wind. But starting from here, the wind can blow this whole direction. It loops around over here, and it generates large waves because it has such a large fetch. So these westerly winds blow over this water for a very long distance, generating very large waves. And this makes these waters, these oceans waters, the bottom of the planet, very dangerous because of the large fetch that the westerlies have, because of the absence of any significant continental land masses. So whenever you have waves of different wavelengths moving through the same sea surface, it creates what's known as interference. Okay. Interference is whenever waves meet up and they basically add with one another. And there's two different ways in which waves can interfere. You can have destructive interference and constructive interference. Destructive interference is whenever two waves interact with each other in a manner that they cancel each other out, resulting in a reduced wave or no wave at all. Where constructive interference is whenever the waves interact with one another and that they produce an additive result where the resulting wave is larger than the two waves themselves that are interacting with one another. And this constructive interference can create what's known as rogue waves, which are these freak waves that occur due to constructive interference of waves in the ocean, and they result in a wave that's larger than the theoretical maximum size of a wave for the current wind conditions. So here we see an image of two waves, this red and blue wave, and so these waves have slightly different frequency. And so because they have slightly different frequency, the waves here are lining up. They're said to be in phase, where you have a crest aligns with a crest. And so they add together in what's called constructive interference, and the resulting wave, this green wave, is larger than the blue and the red wave individually. This is constructive interference. Here at location 2, you see the waves are not lined up. They're said to be out of phase, where the crest of one wave is lining up with the trough of another, so they are, in a sense, canceling each other out. They're destructively interfering, producing a reduced wave. Now over here, they're in phase again, constructively interfering. So this constructive or destructive interference can create patterns in the sea surface, and it's constructive interference that results in rogue waves. So this is a wave record at an oil platform in the North Sea in January 1995. So this is the sea surface elevation in meters. So you can see this is the mean sea surface height at 0. And so this is a crest, trough, crest, trough, crest, trough, crest, trough. And you can see there's multiple waves in there because it's not just one clean wave. There's multiple waves interfering with each other. Okay, but then right here, at this time, a wave passed by that had a very large wave height, about 18 meters, where the normal wave height was somewhere between 4 and 8, maybe around 6 meters. So this is a rogue wave caused by the constructive interference of waves. And just so you know, it's 18.5 meters, that's about 60 feet. And for commercial buildings, each story is about 10 feet. So a 60-foot wave, that's the wave crest, that's about 6 stories high. It's a very large wave. And here's actually a picture of a rogue wave taken aboard a ship. So rogue waves, they cannot be predicted. You could have actually nice, calm weather. You just happen to have waves passing through the ocean that constructively interfere for that brief moment in time at that location, creating a rogue wave. That if you're in that wrong place at that wrong time, that rogue wave can be very destructive. So rogue waves cannot be predicted, and they can be very dangerous. So deep water waves, they transition into shallow water waves as they approach the shore. So out here, the wave is a deep water wave because the water depth is greater than half the wavelength. But as the wave comes in and the water gets shallower, the wave transitions and becomes a shallow water wave. And several things happen to the wave as it moves landward. Because the water molecules, when move in a circular motion, they are slowed down when they move along the sea floor because of friction. They're slowed down. And as a result, these water molecules slow down the water molecules above them, or slows down the water molecules above them, and so forth. So as a whole, the wave begins to slow down. It travels at a slower speed as it enters shallower water. Also, the wavelength begins to decrease, so the distance between crests begins to decrease. But since the wavelength is decreasing, the wave height actually increases as it enters shallower water. And because of the friction interaction with the sea floor, that circular path of the water molecules becomes elliptical, and eventually, when the water is shallow enough, the path will actually become horizontal. And the white comber forms whenever the ratio of height to length becomes 1:7, and eventually the wave will actually break when the ratio of height to depth is 3/4. So when the height, say if the height of the wave is 3 meters and the length of the wave is 4 meters, that's whenever the wave will break. And the waves will always eventually break because as they come closer, the wavelength shortens and the wave height increases. So eventually that ratio of wave height to length will reach 3:4, and that wave will break. When that occurs depends on the depth of the water. If the water remains shallow, deep, and it only gets shallow really close to shore, then those waves aren't going to break until they get really close to shore. But if the water is really shallow, then the waves will break further out to sea. And this is how barrier reefs work. If you have a reef out in the water out here, whenever the waves pass by this reef, there's this very shallow water above the reef, and it causes the waves to break way out here. And so all the wave energy is broken up before it gets to the coast. So that's how barrier reefs work. They cause, because of the shallow water over the reef, it causes all the waves to break over the reef, and so you don't have these coherent waves crashing along the shoreline. And sometimes if you have a sandbar offshore, that can cause waves to break offshore as well. So sometimes if you see waves offshore breaking in the distance, that tells you that there's a sandbar or some portion of shallower water further from shore that's causing the waves to break. So once again, as a wave comes inland, the wave slows down, the wave length shortens, and the wave height increases. And eventually the ratio of height to length reaches 3 to 4, and at that point, that's when the wave breaks. It topples over. So waves often refract, or they change direction as they come ashore. So this is because wave lines, or crests, so a wave line is just a line along the crest of a wave, they usually approach shore at an angle. And so the part of the wave front or wave line that's closest to the shore, it's in shallower water, so it slows down. So the part of the wave line that's closer to the shore is now traveling at a slower speed than the part of the wave line that's further from shore. This causes the wave line, or the crest of that wave, to bend, which is called refraction. So here we see the shoreline right here, and these brown dashed lines are depth contours. So this is the water getting deeper, and this depth is this is where the water depth is half of the wavelength. So the waves out here, with wavelength L, they are deep water waves. They do not sense the sea floor. But the parts of the waves that have entered the shallower water, they begin to sense the sea floor, and they begin to slow down as they enter shallower water. Because they're slowing down, while the part of the wave that's still a deep water wave is traveling at the same speed, the wave line actually bends. And this is the refraction of the wave. And this is why waves usually break, and that breaking wave travels along the shore. So the wave will begin to break here, and as this wave moves in, the wave will break, and that breaking wave will travel that way. And that's what allows surfers to ride breaking waves, is because the waves are traveling in at an angle. If the wave traveled in perpendicular to the shoreline, the entire wave front would break at the same time. It wouldn't. The breaking wave wouldn't roll along the wave along the coastline. And so the fact that the wave begins to break at one side of the shoreline and then it moves along to the other side, that's an indication that the waves are coming in at an angle to the shoreline. So here we can see waves refracting around, this is Hilo, Hawaii. So you can see the wave lines, the crests right here.